Welcome to the fascinating world of electronic spectroscopy. In this video, we'll embark on a journey to understand how scientists use light to probe the electronic structure of atoms and molecules. Electronic spectroscopy is a powerful tool in chemistry and physics, allowing us to explore the invisible world of electrons and their transitions. Whether you're a student, a researcher, or simply curious, this introduction will set the stage for a deeper dive into the principles, techniques, and applications of electronic spectroscopy. Let's begin by understanding what spectroscopy is and why it's so important in modern science. Spectroscopy is the study of how matter interacts with electromagnetic radiation. When light interacts with a substance, it can be absorbed, emitted, or scattered, revealing valuable information about the substance's structure and properties. Electronic spectroscopy specifically focuses on the transitions of electrons between energy levels within atoms or molecules. By analyzing the resulting spectra, scientists can deduce details about electronic configurations, bonding, and even molecular dynamics. This foundational concept is key to understanding the rest of our exploration. Electromagnetic spectrum encompasses all types of electromagnetic radiation, from radio waves to gamma rays. Electronic spectroscopy typically involves the ultraviolet, UV, visible, and sometimes near-infrared regions of the spectrum. These regions are particularly important because the energy of photons in these ranges matches the energy differences between electronic states in atoms and molecules. Understanding the electromagnetic spectrum is essential for grasping how electronic spectroscopy works and what information it can provide. At the heart of electronic spectroscopy are electronic transitions. When a molecule or atom absorbs a photon of the right energy, an electron can jump from a lower energy level to a higher one. This process is called excitation. Conversely, when an electron falls back to a lower energy level, it can emit a photon, producing emission spectra. These transitions are quantized, meaning only specific energy differences are allowed, leading to characteristic absorption or emission lines in the spectrum. Electronic spectroscopy can be divided into absorption and emission spectroscopy. In absorption spectroscopy, we measure how much light is absorbed by a sample at different wavelengths. This tells us which electronic transitions are possible. In emission spectroscopy, we observe the light emitted by excited atoms or molecules as they return to lower energy states. Both methods provide complementary information about the electronic structure of the sample. To perform electronic spectroscopy, scientists use specialized instruments such as spectrophotometers and fluorometers. These devices are designed to precisely measure the intensity of light absorbed or emitted by a sample across a range of wavelengths. Modern instruments often include advanced detectors and computer interfaces, allowing for rapid data collection and analysis. The choice of instrument depends on the type of spectroscopy and the specific information sought. Proper sample preparation is crucial for obtaining reliable electronic spectra. Samples may be in the form of solutions, solids, or gases, depending on the experiment. The concentration, purity, and solvent choice can all affect the results. Careful handling and preparation ensure that the spectra accurately reflect the electronic properties of the substance being studied. This step is often overlooked, but is essential for high-quality data. Electronic transitions often involve movement of electrons between molecular orbitals. In molecules, these orbitals are regions where electrons are likely to be found. The most common transitions are from bonding to antibonding orbitals, such as pi to pi or n to pi asterisk. Understanding molecular orbitals helps explain why certain wavelengths of light are absorbed or emitted, and why different molecules have unique spectra. Not all electronic transitions are allowed. Selection rules based on quantum mechanics determine which transitions can occur. These rules depend on factors like spin and symmetry. For example, transitions that involve a change in spin state are often forbidden while others are allowed. Selection rules help explain the intensity and position of spectral lines, making them a fundamental concept in electronic spectroscopy. One of the most common types of electronic spectroscopy is UV visible spectroscopy. This technique measures the absorption of ultraviolet and visible light by sample. It's widely used to study organic and inorganic compounds, providing information about conjugated systems, transition metal complexes, and more. UV spectroscopy is valued for its simplicity, speed, and versatility in both research and industry. Fluorescence spectroscopy is another important branch of electronic spectroscopy. Here, a sample absorbs light and then emits it at a longer wavelength. This technique is extremely sensitive and is used to detect trace amounts of substances, study biological molecules, and monitor chemical reactions. Fluorescence spectroscopy has revolutionized fields like biochemistry and medical diagnostics. Phosphorescence is similar to fluorescence but involves a delayed emission of light. After absorbing energy, the electron enters a metastable state and takes longer to return to the ground state, emitting light over a longer period. This property is used in glow-in-the-dark materials and in studying certain chemical and biological processes. Phosphorescence provides unique insights into molecular dynamics and energy transfer. Electronic spectroscopy is a cornerstone of modern chemistry. It's used to identify compounds, determine concentrations, and study reaction mechanisms. For example, chemists use UV spectroscopy to monitor the progress of reactions or to analyze the purity of samples. The ability to probe electronic structure makes spectroscopy an indispensable tool in analytical and physical chemistry. In physics, electronic spectroscopy helps unravel the fundamental properties of atoms and molecules. It's used to measure energy levels, study atomic structure, and explore quantum phenomena. Spectroscopy has played a key role in the development of quantum mechanics and continues to be vital in fields like astrophysics, where it's used to analyze the composition of stars and galaxies. Electronic spectroscopy is widely used in biology and medicine. It helps study proteins, nucleic acids, and other biomolecules. Techniques like fluorescence spectroscopy are essential for imaging cells, diagnosing diseases, and tracking biological processes in real time. The non-destructive nature of these methods makes them ideal for sensitive biological samples. Environmental scientists use electronic spectroscopy to detect pollutants, monitor air and water quality, and study atmospheric processes. By analyzing the absorption or emission spectra of environmental samples, researchers can identify contaminants and track changes over time. This application is crucial for ensuring public health and understanding environmental changes. Industries rely on electronic spectroscopy for quality control, process monitoring, and product development. For example, manufacturers use UV-vis spectroscopy to ensure the consistency of dyes, paints, and pharmaceuticals. The speed and accuracy of spectroscopic analysis make it an essential part of modern manufacturing and quality assurance. Astronomers use electronic spectroscopy to study the composition and motion of celestial bodies. By analyzing the light from stars and galaxies, they can determine the elements present, measure redshifts, and even estimate distances. Spectroscopy has been instrumental in discovering exoplanets and understanding the evolution of the universe. Electronic spectroscopy provides insights into energy transfer processes within molecules and materials. By studying how energy moves between different parts of a system, scientists can design better solar cells, light-emitting devices, and sensors. Understanding these processes is key to advancing renewable energy and optoelectronic technologies. Spectral resolution refers to the ability of a spectroscopic instrument to distinguish between closely spaced energy levels or spectral lines. High-resolution instruments can reveal fine details in spectra, such as splitting due to interactions between electrons and nuclei. This level of detail is important for advanced research and precise measurements. Accurate electronic spectroscopy requires careful calibration using known standards. Calibration ensures that the instrument's readings are reliable and reproducible. Scientists use reference materials with well-characterized spectra to adjust their instruments, allowing for meaningful comparisons between different experiments and laboratories. When spectra are collected, data analysis is essential. Scientists use various techniques to interpret the results, such as baseline correction, peak fitting, and deconvolution. Advanced software tools help extract meaningful information from complex spectra, enabling researchers to draw accurate conclusions about the sample's electronic structure. Despite its power, electronic spectroscopy has limitations. Overlapping spectral lines, low sensitivity for certain transitions, and interference from impurities can complicate analysis. Researchers must carefully design experiments and interpret data to overcome these challenges. Ongoing advances in instrumentation and methods continue to expand the capabilities of electronic spectroscopy. Recent years have seen remarkable advances in electronic spectroscopy. New light sources, detectors, and computational methods have improved sensitivity, resolution, and speed. Techniques like ultrafast spectroscopy allow scientists to observe electronic processes in real time, opening new frontiers in chemistry, physics, and materials science. Ultrafast spectroscopy uses extremely short laser pulses to study rapid electronic processes. This technique can capture events that occur in femtoseconds, such as electron transfer and bond breaking. Ultrafast methods have revolutionized our understanding of chemical dynamics and are at the forefront of modern research. Time-resolved spectroscopy allows scientists to follow changes in electronic structure over time. By taking snapshots at different moments, researchers can build a detailed picture of dynamic processes, such as energy transfer, chemical reactions, and molecular rearrangements. This approach provides a deeper understanding of how systems evolve. Computational methods are increasingly used to simulate and interpret electronic spectra. By modeling the electronic structure of molecules, scientists can predict spectra and compare them with experimental data. This synergy between theory and experiment accelerates discovery and helps explain complex observations. Materials scientists use electronic spectroscopy to study semiconductors, polymers, and nanomaterials. By probing electronic transitions, they can optimize materials for electronics, photonics, and energy applications. Spectroscopy helps reveal defects, band structure, and other properties critical for material performance. Nanotechnology relies on electronic spectroscopy to characterize nanoparticles, quantum dots, and nanowires. These materials have unique electronic properties due to their small size. Spectroscopy provides insights into their behavior, enabling the development of new devices and applications in electronics, medicine, and energy. Art historians and archaeologists use electronic spectroscopy to analyze pigments, dyes, and artifacts. Non-destructive analysis reveals the composition and age of materials, helping to authenticate artworks and uncover historical techniques. Spectroscopy bridges science and the humanities, offering new perspectives on cultural heritage. Forensic scientists use electronic spectroscopy to analyze evidence such as fibers, paints, and biological samples. The technique provides rapid, accurate identification, supporting criminal investigations and legal proceedings. Spectroscopy's sensitivity and specificity make it a valuable tool in forensic science. Food scientists use electronic spectroscopy to assess quality, detect contaminants, and monitor processing. By analyzing the spectra of food samples, they can ensure safety and compliance with regulations. Spectroscopy is also used to study the nutritional content and shelf life of food products. Pharmaceutical industry relies on electronic spectroscopy for drug development and quality control. Spectroscopic analysis ensures the identity, purity, and concentration of active ingredients. It also helps monitor stability and detect impurities, safeguarding the safety and efficacy of medicines. Electronic spectroscopy is a staple in science education. Students use spectroscopic experiments to learn about atomic and molecular structure, chemical reactions, and analytical techniques. Hands-on experience with spectroscopy fosters critical thinking and a deeper appreciation for the scientific method. Safety is paramount when working with electronic spectroscopy. Proper handling of chemicals, lasers, and electrical equipment is essential to prevent accidents. Wearing protective gear, following protocols, and maintaining equipment ensure a safe and productive laboratory environment for all researchers. Future of electronic spectroscopy is bright, with ongoing innovations in instrumentation, data analysis, and applications. Emerging trends include miniaturized devices, portable spectrometers, and integration with artificial intelligence. These advances promise to make spectroscopy even more accessible and powerful in the years ahead. Portable spectroscopy devices are transforming fieldwork and on-site analysis. These compact instruments allow scientists to perform rapid, non-destructive measurements outside the laboratory. Applications range from environmental monitoring to food safety and forensic investigations, making spectroscopy more versatile than ever. Artificial intelligence is increasingly being used to analyze spectroscopic data. Machine learning algorithms can identify patterns, classify samples, and even predict outcomes based on spectral information. This integration enhances the speed and accuracy of analysis, opening new possibilities for research and industry. Quantum computing holds promise for revolutionizing spectroscopic analysis. With the ability to simulate complex quantum systems, quantum computers could provide unprecedented insights into electronic structure and dynamics. While still in its early stages, this field represents an exciting frontier for spectroscopy research. Electronic spectroscopy isn't just for scientists, it impacts our daily lives in many ways. From the colors in our clothes to the screens on our devices, spectroscopic principles are at work. Even the analysis of food, water, and air quality relies on these techniques, highlighting their importance beyond the laboratory. Many groundbreaking discoveries have been made using electronic spectroscopy. For example, the identification of helium in the sun, the understanding of photosynthesis, and the development of quantum mechanics all relied on spectroscopic techniques. These achievements underscore the profound impact of spectroscopy on science and society. Several Nobel Prizes have been awarded for advances in spectroscopy. These honors recognize the development of new techniques, discoveries about atomic and molecular structure, and innovations that have transformed science. The legacy of these achievements continues to inspire new generations of researchers. The impact of electronic spectroscopy extends beyond science, influencing technology, industry, and society. From environmental protection to healthcare and communication, spectroscopic techniques play a vital role in addressing global challenges and improving quality of life for people everywhere. Let's recap what we've learned about electronic spectroscopy. We explored its principles, techniques, and wide-ranging applications in science and industry. From probing atomic structure to driving innovation in technology, electronic spectroscopy remains a cornerstone of modern research. Its ongoing evolution promises even greater discoveries in the future. As we look to the future, electronic spectroscopy will continue to shape our understanding of the world. With new technologies, interdisciplinary research, and global collaboration, the possibilities are endless. Whether in the lab, the field, or everyday life, spectroscopy will remain a vital tool for discovery and progress.